又正常待着。我说你没啥要喜欢我可以这样的，因为我们两个孩子对牙都不好，不敢让他吃太多。
All right.
所以我吃偷着给别人，他不让给。
In the next section, we're just going to do some, we're going to through a formula manipulation to show that the internal energy during the formation of an object or of a small cube, as this cube deforms, then the internal energy stored inside that cube, which is equivalent to K dx actually is equivalent to kx dx in a spring. So the rate of change of energy in a spring is equal to kx dx, because this is kx and this is kx dx. So this the rate of change of potential energy in a spring is equal to kx dx. Now the equivalent, if I have this three-dimensional spring made out of a material, the material acts like a spring, where as I'm deforming it, and there is energy that's stored, then this energy is equal to sigma 1 d epsilon 1, sigma 2 d epsilon 2, and so on. So this energy is equal to sigma ij d epsilon ij. So to prove this, there's just it's going to take us just perhaps 10 to 15 minutes to go through the proofs. So bear with me. And it's a very good exercise that you do this by hand for both section 7.2.1 and this next section as well, 7.2.2. So I recommend that you do it by hand. I still, I mean, it's easier for me to do it in the office where no one is looking at me, but it's different when there's a class. But hopefully it will be okay. So, in order to start this, I'm going to right away find what I call u dot multiplied by the volume, which is equal to the total power of the forces acting on the object. So the total power of the forces acting on the object is equal to the force multiplied by the velocity. This is equal to forces multiplied by velocities. Summed each force multiplied by the corresponding velocity. And let's look at what forces we have and what velocities we have. So if this face has stress sigma on 1, then the other face has stress sigma on 1 plus a little bit more. If this face is moving horizontally with a velocity v1, then this face is moving with a velocity v1 plus partial v1 by partial x1 dx1. And if the force acting on this object is rho v1, the velocity of this object is around v1. So the total power due to sigma on 1 and rho v1 is equal to the force multiplied by the velocity. Sigma on 1 multiplied by v1 minus sigma on 1 multiplied by v1 will cancel out. Then you will get sigma on 1 multiplied by partial v1 by partial x1 dx1 plus partial sigma 1 by partial x1 multiplied by v1, which will equal to partial v1 for sigma on 1, v1 by partial x1 multiplied by dx1 multiplied by the area, which is dx2 dx3 plus rho b1 multiplied by b1. This term comes from you have got sigma on 1 v1, sigma on 1 v1 cancel out, and you have sigma on 1 multiplied by partial v1 by partial x1 plus v1 multiplied by partial sigma 1 partial x1. So you get this term, and we'll multiply this by this, you get a very small term that can be ignored, and that's equal to 0. And similarly for sigma 2, 2 and rho b2, and sigma 3, 3 and rho b3, which is equal to, just to replace sigma 1 with 2, 2, and rho b1 with rho b2, and v1 with v2 and x1. So this will be equal to partial sigma 2, 2, v2 with partial x2 plus rho b2 multiplied by dx1, dx2, dx3. So these are the total power acting on that object due to sigma 1, sigma 2, 2, sigma 3, 3, rho b1, rho b2, and rho b3. So now we're left with the shear components. If this is sigma 1, 2, and this is the vertical velocity v2, then this is sigma 1, 2 plus a little bit more, and the velocity here is v2 plus partial v2 partial x1. How much v2 changes with respect to x1 multiplied by dx1. So the total power due to sigma 1, 2 will be equal to sigma 1, 2 multiplied by v2 minus, or this is in a negative, sigma 1, 2 multiplied by v2, these will cancel each other, and you're going to be left with partial sigma 1, 2 multiplied by partial v2 by partial x1 plus partial sigma 1, 2 with partial x1 multiplied by v2. So you are going to get partial sigma 1, 2 v2 by partial x1. And this is multiplied by dx1 and multiplied by dx2 and dx3. And so on for sigma 1, 3 and sigma 2, 3 and sigma 3, 1 and sigma 3, 2. And sigma 2, 1. And so you end up with a total power that looks like this. Partial sigma ij vi by partial x vj by partial xi plus the sum rho bi vi, where dv here is equal to dx1, dx2, dx3. This, by definition, is equal to the divergence of sigma v, and this is the dot product between rho b and v. Now, we already know the following. We know that the divergence of sigma plus rho b is equal to rho A. From equilibrium, we know that the divergence of sigma plus rho B is equal to rho A. So I'm going to utilize this here to show the following. This is partial sigma Ji, partial xg plus rho bi is equal to rho ai. Now the total power is equal to partial sigma Ji bi partial xg plus rho bi equal to partial sigma Gi and partial xg Vi plus rho Vi plus partial for sigma Gi partial Vi by partial xg. This and this are equal to rho ai. I'm going to put the rho ai, Vi plus sigma Ji partial Vi and partial xg. So using the equilibrium equation, I find that the total power per unit volume, I should multiply by the volume, but this is the total power per unit volume. The volume is equal to dx1, dx2, dx3, but I divided by dx1, dx2, dx3. Actually, let's keep the volume, just to be consistent. And now, what we're claiming is that this is equal to the total energy, or the total rate of change of the energy, and that this is equal to the kinetic energy dot plus the potential energy dot. So what we want to prove now is this is indeed the potential energy, or the rate of change of potential energy. And if this is true, indeed, the rate of change of the potential energy, then this is the rate of change of the potential energy. And then this would be what I'm looking for. So I want to show that this is the potential energy is equal to this term. So if the kinetic energy is equal to half rho V dot V integrated over the volume, kinetic energy dot is equal to d by dt of this. Now here everything is changing with respect to the time. So I'm going to keep here d by dt and try to make things not a function of time. So rho is a function of time, v is a function of time, dv is a function of time, but I'm going to use the deformation gradient, the j, and fix dv, where j was equal to dv, small dv over capital dv. This will be equal to half d rho j by dt v dot v dv, where dv is the volume, plus rho v dot v g dv. Now from mass equilibrium, this will go mass equilibrium. So check the mass equilibrium that we studied earlier. And so indeed, the rate of change of the kinetic energy is equal to it's equal to rho A dot V integrated over the volume. So this is indeed the kinetic energy. So indeed, the remaining part is what I call the strain, the strain energy, so the potential energy. And I'm going to call it U dot. And I'm going to divide by the volume. It's equal to sigma Ji partially I by partial x. And let's just look at this for a second. The stress is symmetric. Because the stress is symmetric, and of course there is a summation here. J, I sum from 1 to 3, and J is summed from 1 to 3. The stress is symmetric, so that means I can write it like this. Either or, it's the same. I can also do the following. I can even write it like this. Because of the symmetry of the stress, I can do it like that. Because the stress is symmetric, I can take the symmetric component of that, or because these two are the same, I can replace this side with sigma ij, partial Vj by partial xi. And so sigma, so all those three are equal. Now, do you remember what this thing is? You had a midterm last week. So this was the velocity gradient. So, and sigma ij, partial Vi by partial xj, you can look at it as the trace of sigma L, or trace of sigma. The rate of change of energy is equal to the trace of those two matrices, sigma multiplied by L, or sigma multiplied by D. So I can take the symmetric component, or not the symmetric component, or the actual L itself, and the trace of either this or that will give me the rate of change of energy, or internal energy inside the object, as the object is moving. This is also equal to the sigma, because by the properties of the trace. Now this is a very instantaneous. Now let's try to understand what D is. D is equal to half Dij is equal to half partial Vi by partial xj plus partial Vj by partial xi. And let's look at what the epsilon ij equal to. Epsilon ij was defined, the small strain was defined as, if you remember, was equal to half partial U I by partial capital xj plus partial uj by partial capital xi. This was the initial definition of the strain matrix, the small strain matrix. But if I define the strain according to the current coord system, instead of capital X, I use small x, then as the object is moving and as it's being strained, d epsilon ij is in fact equal to dij multiplied by dt, which is equal to half partial. I'm going to put bi dt here. Partial xj plus partial bj dt by partial xi, which is equal to half partial dui partial xj plus partial dj So as the object is deforming and developing strain, the energy du is equal to sigma ij dij dt, which is basically sigma ij d epsilon ij. And this is what we want to prove. That the internal energy, so let's just go back again and see what we started from. We found the total power acting on this object, and we said that this total power, we utilized a lot of formulas, or a lot of formula manipulations to show that the total power is equal to two quantities. One quantity happens to be the kinetic energy, the other quantity I'm going to call the potential energy, the rate of change of potential energy of the continuum, or the internal energy. When I further analyze that internal energy, it turns out to be equal to sigma ij d epsilon ij. So this is equal to the internal energy as the object is deformed. Now, this there's a term that's always used, energy conjugates. This stress and this strain measure, or this stress and this measure of deformation d, are called energy conjugates. They're called energy conjugates because when you multiply them by each other, you get the amount of energy that the object the object stores as it deforms. Now this energy, you can use other forms of stresses. Let's say, what if I use the Piola-Kirchhoff stress? Now the Piola-Kirchhoff stress is equal to, so the sigma was equal to 1 over j f p transpose. I would like to know what is the energy conjugate to this p. So I'm going to say u prime. So u dot was equal to trace L sigma. L was equal to f dot f negative 1. Sigma is equal to 1 over j f p transpose. So you get 1 over j trace f dot p transpose. And if W, which is the is equal to u dot, W dot is equal to u dot multiplied by the current volume divided by the initial volume, which is equal to j over j trace f dot p transpose, and you get the energy per unit volume of the reference configuration is equal to the trace of f transpose p, f dot p transpose, and dw from this is equal to p multiplied with df ij. and these two are called energy constants. Now, you have some bonus exercises, a lot of bonus exercises in this section. You will see them, some of them, in your final. And they're simple. All the bonus exercises in this section, you should be able to do it. If you're not able to do it, then ask me. Okay, so I'm going to repeat what we did again. Derivation using integration over the continuum quality. So I'm going to repeat the whole thing again, but the difference between what I did before and what I'm doing now is my initial volume. So at the beginning I started with, I looked at my object and I extracted a very small cube and I did work everything on that cube. Now I'm going to do the same thing again, but instead of working on that cube, I'm going to work on the whole object. And I'm going just to follow the same idea. I'm going to find the external power acting on the object, and I'm going to divide that external power into two forms. One form is, I'm going to show that it's the kinetic energy, and the other form I'm going to take it and call it the internal energy that's stored inside the object as it deforms. So as this object is deforming, the external power, or the power supplied by the external forces, is equal to the external force rho b dot the velocity plus Tn, which is the stresses on the boundaries, dot V integrated over the boundary. So I'm going to show the external power is equal to rho B dot V, where dV is the volume, plus sigma transpose N dot V ds. This is equal to rho B dot V dV. I'm going to utilize the components here because it's easier for me. This is sigma j, ji, and j, vi, ds. Sigma gi and jvi, I'm going to utilize the divergence theorem to show this is equal to partial sigma gi vi by partial xg, but now integrated over the volume. And these are the same. I'm just going to go up to show you that this was exactly what we obtained here. The total power is equal to this. It's exactly what we obtained earlier. And again, utilize equilibrium equations, which is partial sigma ji and partial xj plus rho bi is equal to rho ai. When you utilize this, you will get that the external power supplied is equal to the integral of rho v dot v integrated over the volume plus trace sigma L integrated over the volume, following exactly what we did earlier. The difference is I'm just looking at the whole object rather than just one cube, and because dV is arbitrary, and the kinetic energy dot is equal to rho V dot V, you get the internal energy dot is equal to trace sigma, and everything else follows. So again, I ask you to do this by hand, just because it will train you for similar problems that you might see in the final exam. Okay, so now we know the following: that the energy dot is equal to sigma ij d epsilon ij u dot dt, which is equal to d. What is u? This is the question that I'm looking for. I have the rate of change of u, but what is u? So, what possible expressions can I have for u? Now this is in general and doesn't need to be elastic. The material does not need to be elastic. But if the material is elastic, then the total energy is independent of the path, which means sigma j has to be equal to partial u by partial epsilon ij. And similarly, when we said that dw is equal to p multiplied by df multiplied by df ij, again, for this to be independent of the path, P ij has to be equal to partial w by partial f ij. So I'm going to realize this for finding expressions for the strain energy density functions. So for linear, for small, in strain, so strain energy density for linear elastic materials. For linear elastic materials, we already described the constitutive laws in the previous chapter. The energy, the expression for the energy, sorry, chapter 5, the expression for the energy is equal to half sigma j epsilon ij. I have a relationship between the stresses and the strains. I know that the strains, the strain vector is equal to a huge matrix full of e's and Poisson's ratios multiplied by the stresses. If I replace the stresses, the strains with the stresses, I get this huge expression. If I replace the strains, the stresses with the strains, I get this huge expression. This is function of Lamé's constants, and this is function for E and D. So this is just an expression. You can try it by hand. You can try to find it by hand. You can try it using Mathematica. But these are just the forms after you substitute whatever values for epsilon for whatever values for sigma. Sorry, whatever values of epsilon as a function of sigma, you get this, or whatever values of epsilon of sigma as a function of whatever values of sigma as a function of epsilon. So you get these large expressions. Now when you look at these expressions, or when you first, let's look at epsilon 1 plus epsilon 2 plus epsilon 3. Let's look at the volumetric stream. We just want to show that the energy stored inside a continuum can be divided into two forms, a volumetric form and a deviatory form. a form that's due to the volumetric stress, due to the hydrostatic stress, and a form due to the deviatoric stress. If I sum epsilon 1, epsilon 2, and epsilon 3, and this is equal to delta V over V, epsilon 1 is equal to sigma 1 over E minus Poisson's ratio sigma 2 plus sigma 3 over E. Similarly, sigma 2 over E minus Poisson's ratio sigma 1 plus sigma 3 over E plus, now epsilon 3 is equal to sigma 3 over E minus Poisson's ratio over E sigma 2 plus sigma 1. This will be equal to sigma 1 plus sigma 2 plus sigma 3 over E multiplied by 1 minus 2 Poisson's ratios, which is equal to the hydrostatic stress over 3 or 3P E 1 minus 2 Poisson's ratio, which if you take all these three together into what we call K, if you take all these together and call them K, is equal to K, P, the hydrostatic stress over K, which is the what we call the bulk modulus. So the volumetric strain is equal to P over T. If P is 0, the volumetric strain is 0. And if P is not 0, then I have volumetric strain. Now when you look at the strain energy, I'm just going to look at the strain energy. When you look at the total energy, you can divide it into two components. So the expressions above can be written as follows. This is equal to the volumetric component plus the deviatoric component. The volumetric component is equal to 1 minus 2 Poisson's ratio over 6E multiplied by the trace sigma squared. And the deviatoric component is equal to von Mises stress squared divided by 6G. So if I have a stress state and I would like to find the volumetric or the deviatoric stress component, the volumetric or the amount of energy stored inside the object, the volumetric energy or the deviatoric energy component, then just substitute into these above equations and you get both about the volumetric and the deviatoric, and their sum has to be equal to the total. Now if I have an orthotropic material, for an orthotropic material, the only thing I can use is 1 over 2 sigma 1, epsilon 1, plus sigma 2, epsilon 2, and so on. So these expressions when I have 1 Young's modulus and Poisson's ratio, these apply to an isotropic material, but once it's an orthotropic material, linear elastic but orthotropic, I have to utilize just the general form, which is sigma 1, epsilon 1, sigma 2, epsilon 2, and so on. So these are just other problems that you can take a look at. So now we know that the energy is equal to sigma ij d epsilon ij. I would like to look at the form of the energy, the total strain energy stored in an Euler-Bernoulli beam. So in an Euler-Bernoulli beam, sigma, the energy per unit volume, when I integrate it over the volume, This is equal to the energy is equal to the integral of sigma ij d epsilon ij. This is integrated over the volume. The volume is dA and dx1. So integrated over the area, integrated over the length of the beam. Sigma ij d epsilon ij, this is a linear elastic, and the only non-zero stress component in the Euler Bernoulli beam, the only non-zero strain component was epsilon 1. So I have sigma on 1 d epsilon on 1. It's linear elastic, so sigma on 1 epsilon 1 over 2 integrated over the area integrated over x. Now epsilon 1 was equal to negative x2 d2y by dx1 squared. So I'm going to put this here. And sigma on 1 was equal to negative m x2 divided by I. Or sigma on 1 is equal to e epsilon 1, whichever you want to use. You put it here. And you get the following forms. Either this, or this. So the energy is equal to the integral of the moment multiplied by the second derivative of y with respect to x1 squared, integrated over the length, or 1 over 2 ei m squared, or ei over 2 d2y by dx1 squared, all squared dx1. So this is the total strain energy in Euler Bernoulli beam. And who's taking 665? This is the form that we use to minimize for finding that when we put this total strain energy in the beam into the potential energy equation, this is one of these forms is the one that we put here. And this is another problem just to calculate the potential energy in an Euler Bernoulli beam. For a Timoshenko beam, again, I'm not going to ask you about Timoshenko beams in the final exam, but if you want to look at Timoshenko beams, the difference between a Timoshenko beam and an Euler Bernoulli beam is that I have sigma on 1 and sigma on 2. So sigma on 1 d epsilon on 1 plus sigma on 2 d epsilon on 2. So you get two components for the energy, one due to sigma on 1 and one due to the shear. That's why there are two terms. One because of the shear deformation, and one due to the bending deformation. Okay, so now we'll give you another 5 minutes.